Ever wondered how your body keeps every single cell perfectly hydrated and, bathed in just the right chemical soup?
Yeah, it's not magic, right? It's this incredible feat of physiological engineering happening constantly.
Absolutely. So today we're taking a deep dive into transport of solutes and water. This is based on Chapter 5 of Boron and Boulpaep's Medical Physiology.
A classic.
Definitely. Our mission is to really unpack how your body's cells manage their internal environment, keep all those fluids balanced, absorb nutrients, get rid of waste.
All without you consciously doing anything.
Exactly. All automatic.
And, this isn't just theory for an exam. Understanding these fundamentals is, well, it's crucial. It really is the bedrock of clinical medicine.
How so?
Well, think about diagnosing dehydration or even just understanding how different medications actually work at the cellular level. These concepts, they set you up for so many aha moments later on.
Okay, sounds essential. Let's get into it then.
Let's do it.
Okay, let's start with the big picture. Where are all these vital fluids actually located in your body, like the main neighborhoods?
Right. Imagine your body like a city.
Mhm.
You've got two main neighborhoods. There's the intracellular fluid, or ICF, that's everything inside your cell.
Okay, got it.
And then there's the extracellular fluid, the ECF. That's everything outside the cells.
And the cell membranes are like the walls separating those neighborhoods.
Exactly. They're the critical gatekeepers, the barriers between these two worlds.
So how much fluid are we talking about?
Good question. For a typical, say, 70-kilogram adult male, total body water is around 42 liters.
Wow, that's a lot.
It is. But it's not split evenly. Roughly 60% of that, so about 25 liters, is ICF. Most of your body's water is actually inside your cells. The other 40%, about 17 liters, is ECF outside the cells.
And I think I remember reading that women have a slightly lower percentage.
That's right, yeah. Women typically have a lower percentage of total body water, maybe around 50% compared to 60% for men. And it's mostly because women generally have a bit more adipose tissue, fat tissue, which holds less water than muscle does.
Makes sense.
And here's a neat clinical tidbit for you. Acute changes in total body water. You can actually monitor them just by tracking body weight. It's a surprisingly simple but powerful metric.
Interesting. So, okay, that ECF, the 17 liters outside the cells, is it just one big homogeneous pool or?
No, not at all. It's actually got its own internal structure. The ECF itself has three pretty important subcompartments.
Okay, what are they?
First, you've got plasma volume. That's about 3 liters. And it's the fluid within your heart and blood vessel, basically the liquid part of your blood.
Right, the non-cellular part.
Exactly. Plasma makes up about 55% of your total blood volume. The rest is cells, red cells, white cells, platelets. That fraction of cells is what we call the hematocrit.
Okay, plasma. What's next?
Second, and this is the biggest ECF compartment, is the interstitial fluid. That's about 13 liters.
13? Wow.
Yeah, it's the fluid that directly bathes most of your body's cells. It literally fills the spaces between cells, but outside the blood vessels. The capillary walls are the barriers separating this interstitial fluid from the plasma.
Okay, so plasma in vessels, interstitial fluid bathing cells. What's the third one?
The third is a smaller, more specialized compartment called transcellular fluid. It's usually only about 1 liter.
And where's that?
This is fluid that's kind of trapped within specific spaces lined by epithelial cells. Think of the synovial fluid in your joints that keeps them lubricated.
Ugh.
Or the cerebrospinal fluid, CSF, cushioning your brain and spinal cord. What's really fascinating here is how diverse their compositions can be compared to plasma. It hints at their specialized jobs.
So different volumes, different locations. Do they also have, like, dramatically different chemical makeups?
Oh, absolutely. And this difference is critical. It's fundamental to how our cells actually function.
How different are we talking?
Okay, look at the ICF inside the cells. It's remarkably high in potassium K plus A and very low in sodium Na plus and chloride, Cl.
High potassium inside. Got it.
Now, flip that completely for the ECF, which includes both plasma and that interstitial fluid. The ECF is high in sodium and chloride and low in potassium.
So almost the exact opposite.
Pretty much, it's this really dramatic difference, and it's primarily maintained by one protein that's, well, incredibly important, the Na-K pump, sodium-potassium pump.
The Na-K pump, I've definitely heard of that.
We'll be diving much deeper into that pump soon because it's central to almost everything here. It constantly works, pushing sodium out of the cell and pulling potassium into the cell.
Okay. Now, you mentioned plasma earlier. I remember hearing about plasma proteins. Do they mess with these compositions much?
They do, yeah, significantly,
Mm.
especially when you compare plasma directly to the interstitial fluid. The biggest difference is that those large plasma proteins are mostly stuck in the plasma. They can't easily cross the capillary walls to get into the interstitial fluid.
Okay, so they stay in the blood vessel.
Right. And these proteins, they actually take up space, about 7% of the plasma volume, and they carry a net negative charge.
Why does that matter?
Well, here's where it gets really interesting, especially clinically. When a lab reports your sodium level, they usually give a value per liter of plasma solution. But imagine a patient has really high levels of plasma protein or lipids, like in hyperproteinemia or hyperlipemia.
Okay.
Those proteins or lipids are taking up volume. So a reported sodium level might look low, say 122 milliequivalents per liter, but if 20% of that plasma volume is actually protein, the true sodium concentration in the water part of the plasma, the part that actually interacts with cells via the interstitial fluid, could be totally normal, like 153.
Whoa. So the lab value could be misleading.
Potentially, yeah. It matters because it's the composition of the interstitial fluid, which is mostly protein-free, that directly surrounds and affects your cells.
That makes sense.
And there's another effect called the Gibbs-Donnan equilibrium. Because those plasma proteins are negatively charged and trapped in the plasma, they tend to pull positively charged ions, like sodium, slightly into the plasma from the interstitium. And they push negatively charged ions, like chloride, slightly out of the plasma into the interstitium.
So like tiny magnets affecting the small ions.
Kind of. It creates this slight but measurable difference in the concentration of small ions between plasma water and interstitial fluid. It's subtle, but important physiologically.
Okay, so we have these vastly different ion concentrations inside versus outside the cell, but does that mean the overall thickness, like the total particle concentration, is also different?
That's a great question. And surprisingly, the answer is no.
Hmm?
Despite those radical differences in which ions are where, all the body fluid compartments maintain roughly the same osmolality.
Osmolality, what's that exactly?
Osmolality is just the total concentration of all the free particles dissolved in a solution. For us, in our body fluids, it's about 290 milliosmoles per kilogram of water. So 290 millios.
And that's the same inside and outside the cells.
Pretty much, yes, at steady state. So think about it. One glucose molecule counts as one particle. But if you dissolve sodium chloride, NaCl, it breaks into two ions, Na plus and Cl, so that counts as two particles.
Ah, okay. So dissociation matters.
It does. And what's interesting is those big plasma proteins we talked about, even though they're massive, they contribute very little to the total osmolality because compared to the millions and millions of tiny ions and molecules, there just aren't that many protein molecules.
Okay, so osmolality is balanced. What about electrical charges? You mentioned proteins are negative. Does everything need to balance out electrically?
Absolutely. That's the principle of electroneutrality. In any overall solution compartment, the total number of positive charges has to equal the total number of negative charges. It has to be neutral overall.
How does that work inside the cell with all that potassium?
Right. Inside the cell, the ICF, the positive charge from potassium and the little bit of sodium far exceeds the negative charge from common ions like chloride or bicarbonate. So what makes up the difference?
The proteins again?
Exactly. And other things like organic phosphates. These large intracellular molecules carry a net negative charge, and they provide the balance needed for electroneutrality inside the cell.
And what about in the plasma? Is there a similar concept?
Yes, and it's clinically very important. In blood plasma, the difference between the commonly measured positive ions, mostly sodium, and the commonly measured negative ions, mostly chloride and bicarbonate, is called the anion gap.
Onion gap. Okay.
A normal anion gap is usually somewhere between 9 and 14 milliequivalents per liter. It represents the concentration of unmeasured anions, mostly those plasma proteins we discussed, but also things like phosphate, sulfate, and organic anions.
So why is that clinically important?
Well, think about certain disease states. For example, in type 1 diabetes, if insulin levels are very low, the body starts breaking down fats and producing acidic byproducts called ketoacids, like acetoacetate and beta-hydroxybutyrate.
Okay.
These ketoacids are negatively charged anions. They aren't usually measured in the standard electrolyte panel, so they build up in the plasma and cause the anion gap to increase dramatically. It's a key diagnostic clue.
Ah, I see. So a high anion gap can signal that kind of metabolic problem.
Precisely.
So it sounds like keeping these balances, osmolality, electroneutrality, specific ion concentrations is incredibly important. What happens if things go wrong?
Well, the consequences can be severe, even life-threatening. For instance, even small changes in the concentration of potassium outside the cell in the ECF can cause dangerous heart rhythm disturbances.
Wow.
Yeah. And similarly, if the sodium concentration in the ECF becomes abnormal, it messes with the osmolality balance. Water can then shift dramatically into or out of brain cells. Too much water influx causes brain swelling, edema, which can lead to seizures, coma,
Or even death.
or even death. And if water rushes out, the brain cells shrink, which is also incredibly dangerous. So this really underscores why understanding how the body controls these fluid compartments isn't just academic, it's absolutely vital for patient care.
Okay, that really drives the point home. So we know where the fluids are, what's in them, and why balance is crucial. Now let's get to the how. How do ions and molecules actually move across those cell membranes and capillary walls? Let's start with passive transport, the easy way.
Right, passive transport, think of it like water flowing downhill or through a breach in a dike, as you said. A substance moves passively across a membrane if two conditions are met. One, there's an open pathway for it.
Okay, a door needs to be open.
Exactly. And two, there's a favorable electrochemical gradient. That's the driving force.
Electrochemical gradient. Break that down for me.
Sure, that's the chemical part. But for charged things, like ions, there's also an electrical potential energy difference. This is the voltage difference across the membrane. Positive ions are pushed away from positive areas and attracted to negative areas, and vice versa for negative ions.
So the electrochemical gradient combines both the concentration difference and the electrical difference.
Precisely. It's the sum of those two forces that determines the overall direction and magnitude of the driving force for an ion.
And with passive movement, it's always downhill along this combined gradient.
Always. The net movement is always down the electrochemical gradient. Like a ball rolling downhill, it's seeking the lowest energy state.
What about equilibrium? Does movement stop then?
Not exactly. At equilibrium, there's no net movement. But particles are still moving back and forth across the membrane. It's just that the rate of movement in one direction perfectly balances the rate in the opposite direction.
Yeah.
And whenever there is net passive transport happening, it's always heading back towards that equilibrium state.
You mentioned ions. Is there a way to predict when an ion will be at equilibrium?
Yes, there is.
Yeah.
For ions, the equilibrium point is described by a very important equation called the Nernst equation.
The Nernst equation.
The Nernst equation tells you the exact membrane voltage, called the equilibrium potential for that ion, at which the electrical force perfectly balances the chemical concentration force for that specific ion. At that voltage, there's no net movement of the ion.
Okay, can you give an example?
Sure. Let's say you have a 10-fold gradient for potassium ions, maybe 100 millimolar inside the cell and 10 millimole outside. The Nernst equation predicts that potassium would be at equilibrium if the membrane voltage were exactly negative 60 millivolts inside relative to outside.
So if the cell's voltage was a negative 60 milliV, potassium wouldn't have a net urge to move in or out.
Exactly, assuming only those forces are acting on it.
So applying that logic for a typical cell, maybe with that resting membrane voltage around negative 60 milliV, what does the Nernst concept tell us about the net driving forces for the key ions we talked about earlier? Like, which way do they really want to go?
Okay, let's look at that. For sodium, Nat+, remember, it's highly concentrated outside and low inside, and the inside is electrically negative. Both forces push it inwards. So the net driving force for sodium is huge, maybe around megas 121 millivolts. It desperately wants to get into the cell.
Minus 121 millivolts. That sounds like a lot of force.
It is. Now, potassium, K+. It's concentrated inside. The negative inside pulls it in. The concentration gradient pushes it out. The concentration gradient usually wins slightly, so there's a net driving force outwards, but it's much smaller, maybe around plus 28 millivolts.
So potassium wants to leave, but not as desperately as sodium wants to enter.
Good way to put it. Then there's calcium, Ca2+. It's kept at incredibly low concentrations inside the cell, plus the inside is negative. So like sodium, both forces push it inwards. The driving force for calcium is enormous, maybe negative 185 millivolts.
Wow, even stronger than sodium.
Yeah. And finally, chloride, Cl. Its situation is often more complex, depends on the cell type. But typically, the electrical force pushing it out, negative inside repels negative chloride, slightly outweighs the concentration gradient pushing it in. So there's often a small net driving force for chloride to exit the cell, maybe around negative 13 millivolts.
Okay, so knowing the direction and the driving force is one thing, but how fast does this passive movement actually happen? What determines the rate?
The rate depends entirely on the transport mechanism. Most ions and water-loving hydrophilic things can't just slip through the fatty lipid bilayer of the cell membrane.
Right, oil and water don't mix.
Exactly. So the body uses specialized protein pathways embedded in the membrane to help these substances cross.
What kind of pathways are we talking about?
There are three main types of these integral membrane proteins that facilitate passive transport. First, you have pores.
Pores, like tiny holes.
Pretty much. Think of them as always open tubes or tunnels, providing a continuous pathway filled with water across the membrane.
Any examples?
Sure. There are porins in mitochondrial membranes. But the ones most relevant for water balance are the aquaporins, or AQPs. These were discovered by Peter Adrank. He shared a Nobel Prize for it. They're highly specific water channels, just large enough for water molecules to pass through in single file. Really elegant.
Aquaporins for water. Okay. What's the second type?
Second, we have channels. You can think of channels as essentially gated pores.
Gated, so they can open and close.
Exactly. They have a movable barrier, a gate, that opens and closes the pathway. They also have sensors that tell the gate when to open or close, maybe responding to changes in voltage or the binding of a chemical messenger or specific molecule.
So they're regulated.
Highly regulated.
Yeah.
They also have a selectivity filter that determines which specific ions are allowed to pass through when the gate is open. And then there's the pore itself. When a channel is open, lots of ions can flow through very quickly, creating a measurable electrical current.
What are some important channels?
Well, NAP+ channels are absolutely critical. Given that huge inward driving force for sodium, when NAP+ channels open, sodium rushes into the cell rapidly. This is fundamental for generating action potentials, like nerve impulses. They're also key for sodium absorption in places like the kidney, like the ENSC channels.
Okay, sodium channels.
Then you have K+ channels. These play a major role in setting the negative resting membrane voltage in most cells, and also in helping to end action potentials. Sia2+ channels allow rapid calcium entry down at steep gradient, which is crucial for cell signaling and triggering various processes. There are even specialized proton, H+ channels, and various anion channels, like those for chloride, important in epithelial transport and pH regulation.
Pores, channels. What's the third type?
A third type are carriers. Now, carriers are different from pores and channels. They also have binding sites for the specific solutes they transport, but they never offer a continuous path across the membrane.
How do they work then?
They work kind of like a revolving door or maybe a turnstile with two gates. They bind the solute on one side, then undergo a shape change and release the solute on the other side. Crucially, they have at least two gates that are never open at the same time. You bind, one gate closes, the other opens, you release.
And this is still passive transport.
Yes, if it's carrier-mediated facilitated diffusion, it's still passive. It doesn't require direct energy input. It just helps the solute move down its existing electrochemical gradient. But it facilitates or helps the process happen faster than it would otherwise.
Does it have different characteristics than channel transport?
Yes, a key difference from simple diffusion or channel flow is that carrier-mediated transport is saturable.
Saturable, meaning it maxes out.
Exactly. Think of it like having a limited number of revolving doors. Once all the doors are occupied and spinning as fast as they can, you can't increase the transport rate any further, no matter how many more people solutes are waiting outside. There's a maximum transport rate, often called Jmax.
Like enzyme kinetics.
Very similar. The kinetics often follow Michaelis-Menten type behavior. There's a term called CAMM, which is the solute concentration at which transport is half maximal. CAMM tells you something about the carrier's affinity for the solute.
Can you give an example of a carrier?
Sure, a classic one is GLUT1. It's a glucose transporter found in many cells belonging to the SLC2 family. It helps glucose, which is too large and polar to diffuse easily, get into cells down its concentration gradient via facilitated diffusion. Other examples include urea transporters, UTs, and some organic cation transporters, OCTs.
Okay, so pores, channels, and carriers handle passive downhill movement. But what about moving things uphill against their electrochemical gradient? You said that needs energy.
It absolutely does. That's active transport. And it always requires an input of energy to move something against its natural tendency.
Are there different kinds of active transport?
Yes, we generally distinguish between two main types based on where the energy comes from directly.
Okay. What's the first type?
The first is primary active transport. We often just call these pumps. These transporters directly use energy released from a chemical reaction, most commonly the breakdown or hydrolysis of ATP, adenosine triphosphate.
ATP, the cell's energy currency.
Exactly. Think of these pumps like a motor-driven winch directly using fuel, ATP, to lift a heavy weight, the solute, uphill. Because they often break down ATP, they're also known as ATPases.
And you mentioned the NAK pump earlier. Is that one of these?
It is the quintessential example. The NAK pump, or NAK ATPase, is probably the most important primary active transporter in animal cells. It's found in nearly every cell, and it's absolutely critical. Jen Skell got a share of the Nobel Prize in chemistry for discovering it.
So how does it work?
Okay, it's a protein embedded in the plasma membrane. It cycles through different shapes or conformations. Basically, in one complete cycle, it picks up 3 sodium ions from inside the cell.
3 sodium out?
Uses the energy from breaking down one ATP molecule, changes shape,
Yeah.
and releases those 3 sodium ions outside the cell. Then, in its new shape, it picks up 2 potassium ions from outside,
2 potassium then.
changes shape back, and releases the potassium inside the cell. So for every ATP molecule burned, it's 3 Na plus out, 2 K plus in.
And that keeps sodium low inside and potassium high inside.
Precisely. It actively maintains those crucial concentration gradients that we talked about earlier.
You said 3 positive charges out, but only 2 positive charges in. Does that imbalance matter?
It does, because it moves a net of 1 positive charge out of the cell per cycle. 3 out, 2, and a 1 net charge out. The pump itself is electrogenic. It directly contributes a small amount to making the inside of the cell electrically negative relative to the outside.
So it helps create the membrane voltage too.
Yes, it plays a role. And as you can imagine, this pump is a huge energy consumer for the cell. In some tissues, like the kidney, it might account for a third or even more of the total energy used.
Wow. Is there anything that affects its function clinically, I mean?
Yes, very importantly. The NAK pump can be specifically inhibited by a class of drugs called cardiac glycosides. Examples are uabane, used experimentally, and digoxin, used clinically to treat certain heart conditions.
Digoxin inhibits the NAK pump.
It does. And here's a critical clinical correlation you absolutely need to remember. Low levels of potassium in the blood, a condition called hypokalemia, make digitalis toxicity much more likely.
Why is that?
Because potassium ions and cardiac glycosides actually compete for binding to the same site on the outside-facing part of the NAK pump. If potassium levels are low, the drug has less competition, binds more readily, and inhibits the pump more strongly, potentially leading to toxic effects.
Okay, that's a really important connection. Hypokalemia increases digoxin toxicity.
Got it.
Memorize that one.
Are there other important primary active pumps besides the NAK pump? Yes, definitely. There's a whole family of pumps called P-type ATPases, which work in a similar way, getting phosphorylated during their cycle. This family includes the HK pump, proton potassium pump, famous for acidifying the stomach, but also found in the kidney and intestines.
The proton pump inhibitors act on that one, right?
Exactly. Drugs like omeprazole target the gastric HK pump. Then there are the K2 plus pumps. There's PMCA, plasma membrane K2 plus ATPase, which pumps calcium out of the cell, and SERCA, sarcoplasmic endoplasmic reticulum K2 plus ATPase, which pumps calcium into intracellular storage compartments like the ER or SR. These are absolutely vital for keeping the free calcium concentration inside the cell incredibly low.
Okay, P-type pumps. Any other kinds?
Yes, another major class are the F-type ATPases. These look kind of like tiny molecular lollipops. The most famous example is the mitochondrial ATP synthase.
The one that makes ATP. I thought these pumps used ATP.
You caught me. Under normal physiological conditions in the mitochondria, the F-type ATPase actually runs backward compared to the other pumps. It functions as an ATP synthase.
How does it do that?
It's amazing. The stalk part, called Pho, sits in the inner mitochondrial membrane and acts like a tiny turbine. Hydrogen ions, protons, which have been pumped out by the electron transport chain, flow back into the mitochondrial matrix through this Pho turbine, making it rotate.
It actually spins.
It actually spins, and this rotation drives conformational changes in the head part, the F1 portion, which is a little chemical factory that synthesizes ATP from ADP and phosphate. It's called rotary catalysis. Paul Boyer and John Walker shared part of a Nobel Prize for figuring this out.
Wow. And the hydrogen gradient comes from?
That comes from the electron transport chain or respiratory chain, also in the inner mitochondrial membrane. As electrons are passed along, energy is used to pump protons out, creating an electrochemical gradient for protons. Peter Mitchell won the Nobel Prize for proposing this whole idea, the chemiosmotic hypothesis.
Incredible. So F-type can make ATP? Any others?
There are also V-type H+ pumps. These are found on the membranes of intracellular organelles, like lysosomes, endosomes, and Golgi. They pump protons into these organelles, making their interior acidic, which is important for their function, like breaking down waste or sorting proteins.
Okay. And one more big group.
Yes, the ATP binding cassette, or ABC transporters. This is a huge family. They all have a characteristic structure that binds ATP, but they do diverse things. Some are pumps, some act more like channels, some are
Can
regulators.
I Amos examples here?
Clinically, the MDR proteins, multi-drug resistance proteins,
Mm-hmm.
are very important. One example is MDR1, also called P-glycoprotein. It's a pump that actively transports a wide variety of hydrophobic compounds, including many drugs and metabolic byproducts, out of cells.
Why is that clinically relevant?
Well, in cancer treatment, sometimes cancer cells start overexpressing MDR1. This pump can then efficiently pump anti-cancer drugs out of the cell, making the cell resistant to the treatment. It's a major challenge in chemotherapy.
Ah, I see. That's a big problem.
Another really famous ABC transporter is CFTR, the cystic fibrosis transmembrane regulator. It's the protein that's mutated in patients with cystic fibrosis.
And what does CFTR normally do?
It primarily functions as a regulated chloride channel, although it also influences other channels. Its activity is controlled by ATP binding and by phosphorylation, often linked to signaling pathways like those involving cyclic AMP.
Hmm.
When it's defective, chloride transport is impaired, leading to the thick mucus and other problems seen in cystic fibrosis.
Okay, so primary active transport uses ATP directly. You mentioned a second type of active transport.
Right, that's secondary active transport. This is a bit more indirect, but very clever.
How does it work?
Secondary active transport couples the downhill movement of one solute, moving with its favorable electrochemical gradient, to the uphill movement of another solute, moving against its unfavorable gradient.
So one going downhill powers the other one going uphill.
Exactly. Think of it like a seesaw. The downhill movement provides the energy. Crucially, the downhill gradient used is very often the steep, inwardly directed sodium gradient that was established by the primary active transporter, the NAK pump.
Ah, so the NAK pump sets the stage, and these secondary transporters take advantage of that sodium gradient.
Precisely. The NAK pump does the primary work of creating the sodium gradient using ATP, and then the secondary transporters harness the energy stored in that gradient to move other things. No direct ATP breakdown by the secondary transporter itself.
Clever. Are there different kinds of secondary active transport?
Yes, two main types based on the direction the solutes move relative to each other. First, you have cotransporters, which are also called symporters,
Cotransporters, importers,
meaning both solutes, the one moving downhill and the one moving uphill, move across the membrane in the same direction, either both in or both out.
Okay. Example.
A classic, super important example is the Na plus glucose cotransporter, or SGLT. You find these mainly in the lining of your small intestine and in your kidney tubules.
What does SGLT do?
It uses the energy from sodium moving down its gradient
Yeah.
into the cell to pull glucose up its gradient, also into the cell.
Mm.
This is how your body absorbs glucose from your diet or reclaims it from the urine, even when the glucose concentration inside the cell is already higher than outside.
It can really concentrate glucose.
Amazingly so. Some SGLT transporters move 2 sodium ions for every 1 glucose molecule. That coupling allows them to generate an astonishing glucose concentration gradient, potentially up to 10,000-fold.
Wow. Are there other important cotransporters?
Oh yes, there are sodium-driven transporters for amino acids, bicarbonate, like the NBC family, crucial for pH regulation, and ions like the NAKCl cotransporter, NAKCC. NKCC is important in many tissues, including the kidney, and it's the target of powerful loop diuretics like furosemide, Lasix. There's also the NaCl cotransporter, NCC, targeted by thiazide diuretics.
So diuretic drugs often work by blocking these cotransporters in the kidney.
Exactly. There are even some cotransporters driven by proton, H+ gradients, instead of sodium, like PepT1 for absorbing small peptides, or DMT1, which transports divalent metal ions like iron, but can unfortunately also bring in toxic metals like cadmium or lead.
Okay, so cotransporters move things in the same direction. What's the other type of secondary active transport?
The other type are exchangers, also called antiporters.
Exchangers, antiporters, opposite direction.
You got it. Here, the solutes move in opposite directions across the membrane. One moves downhill, providing the energy for the other to move uphill in the reverse direction.
Give me some examples.
A really critical one is the NOCCAT exchanger, NCX. It typically moves 3 sodium ions into the cell downhill in exchange for moving 1 calcium ion out of the cell uphill.
So it helps get calcium out like the PMCA pump.
Yes. It's another major player in keeping intracellular calcium low or restoring low levels after they rise, like during muscle contraction or nerve signaling. It's particularly important when calcium levels get quite high, as it can move calcium faster than the PMCA pump, although maybe not to quite as low a level.
Okay, NCX for calcium. What else?
Another vital one is the Na-H exchanger, NHE. This typically exchanges 1 sodium ion coming in for 1 proton, H+, going out. It's essential for regulating intracellular pH, helping to prevent the cell from becoming too acidic.
NHE for pH. Makes sense.
Then there are antigen exchangers, like the Cl-HCO3 exchanger, also known as AE proteins. These swap chloride for bicarbonate, playing roles in CO2 transport in red blood cells and pH regulation in many other cells. There are many, many other exchangers for various anions, organic molecules, and drugs, too. It's a huge family with diverse roles.
Wow. Okay, that's a massive toolkit of transporters, passive pores, channels, carriers, and then active primary pumps and secondary cotransporters and exchangers. How do they all work together inside a single cell to maintain that specific internal environment we talked about? It must be a coordinated effort.
It truly is a beautifully coordinated symphony, you could say.
Yeah,
And the undisputed conductor, the absolute kingpin, is the NAK pump.
because it sets up the sodium gradient.
Exactly. By constantly working to keep intracellular sodium low and potassium high, it establishes those powerful electrochemical gradients, especially the sodium gradient, that are then harnessed by so many other processes.
Like secondary active transport.
Like secondary active transport, yes. But also, remember, the pump itself is electrogenic, contributing to the negative membrane voltage. That negative voltage, combined with the K plus leak channels allowing potassium to flow out down its gradient, is the primary reason the inside of the cell is negative. And that inside negative voltage, plus that huge inwardly directed chemical gradient for sodium, means sodium is always incredibly eager to enter the cell. The cell captures and uses that potential energy for critical functions.
You mentioned some earlier.
Right. Three key things driven by the NAD plus gradient maintained by the pump. 1. Transepithelial transport, powering the movement of substances across entire cell sheets, like in your gut or kidney. 2. Action potentials. The rapid influx of sodium through voltage-gated channels is the basis of electrical signaling in nerves and muscles. 3. Secondary active transport, driving the uptake of nutrients like glucose and amino acids and the regulation of other ions like calcium and protons.
So the NADK pump is really fundamental.
Absolutely fundamental. Its continuous action is essential for cellular life as we know it.
Now, what about calcium? You said it's kept incredibly low inside, like 10,000 times lower than outside. How does the cell manage that huge gradient, especially since calcium wants to rush in so badly?
Yeah, maintaining that incredibly low resting intracellular calcium level, around 100 nanomolar, is critical because calcium acts as a potent intracellular signal. It's achieved by several players working together.
Which ones?
On the plasma membrane, you have the PMCA K2 plus pump using ATP, and the NACO exchanger, NCX, using the Na plus gradient, actively pumping calcium out.
Okay, pumps and exchangers on the outer membrane.
And inside the cell, you have the Circa pumps located on the membrane of the endoplasmic reticulum, or sarcoplasmic reticulum in muscle. These pumps use ATP to sequester calcium, locking it away inside these organelles, keeping the concentration in the cytoplasm very low.
So it's pumped out and locked up internally.
Exactly. It's a multi-pronged strategy. And the PMCA pump has this neat feature. It gets stimulated by calcium itself via a protein called calmodulin. So when intracellular calcium starts to rise, the pump becomes more active, helping to bring the levels back down efficiently.
Clever design. What about chloride and pH inside the cell?
Chloride levels inside the cell are usually a bit higher than what passive distribution alone would predict. This suggests there are active uptake mechanisms, like maybe ClH-CO3 exchange or sometimes NKCC activity, that balance the passive efflux through chloride channels. And intracellular pH is typically maintained around 7.2. This is actually more alkaline or less acidic than would be expected from passive distribution of protons.
So the cell actively keeps itself less acidic.
Yes, primarily through powerful acid extrusion mechanisms like the NO-H exchanger, NHE, and various NO+ driven bicarbonate transporters that effectively remove acid H+, or bring in base HCO3. These transporters are often stimulated specifically when the cell's interior starts to become too acidic, acting as a feedback control.
Okay, so cells are constantly managing ions and pH. Now let's shift focus slightly. We've talked a lot about solutes, but cells are mostly water. How is water movement controlled? Is it active too?
That's a crucial point.
Yeah.
Water transport is always passive. There are no water pumps in the way we think of ion pumps.
Always passive. So how does it move?
Water moves down its own driving forces. The main driving force across cell membranes is an osmotic gradient. Water flows from an area of lower total solute concentration, higher water concentration, to an area of higher total solute concentration, lower water concentration.
Trying to dilute the more concentrated side?
Exactly. It's trying to equalize the solute concentration, or osmolality, on both sides. When the osmolality is higher outside the cell than inside, water flows out, and the cell shrinks. This process is called osmosis. Water is only at equilibrium across a cell membrane when the osmolality inside and outside is identical.
Hydrostatic pressure, like blood pressure, doesn't play much role for individual cells?
Not usually across the cell membrane itself.
Hmm.
Hydrostatic pressure differences are much more important across capillary walls, driving fluid movement between plasma and interstitial fluid. But for water movement into or out of a typical cell, it's overwhelmingly driven by osmotic differences.
Okay, so if water just follows solutes passively, why don't our cells just swell up and burst all the time? You mentioned earlier there are lots of impermeable, negatively charged proteins inside cells. Wouldn't they constantly pull water in?
That's an excellent question. You're referring to Donnan forces or the Gibbs-Donnan effect applied to the cell. Those impermeant intercellular anions, proteins, organic phosphates, would indeed attract positive ions like Na+ and K+, and consequently, water. Sorry.
But it's not.
It's not, thanks again to our hero, the NAK pump. The pump constantly works against this passive tendency to swell. By actively pumping sodium out of the cell, it effectively removes an osmotically active particle that would otherwise accumulate due to the Donnan effect. This prevents the cell from reaching a true Donnan equilibrium and allows it to maintain a normal volume in a dynamic, steady state.
So the pump isn't just for gradients, it's essential for volume control too.
Absolutely essential. It's sometimes called the pump leak model. Passive leaks let ions and water follow Donnan forces, but the pump actively counteracts this, burning energy to maintain volume.
Amazing. But what if cell volume is suddenly challenged? Like if you become dehydrated, the ECF gets more concentrated, or if you drink way too much pure water, the ECF gets diluted. Can cells fight back in the short term?
Yes, they have sophisticated rapid responses to regulate their volume.
Like what?
If a cell finds itself in a hyperosmotic environment, like the ECS gets too concentrated and starts to shrink, it activates mechanisms for solute uptake. It might turn on things like the NaH exchanger or the NKCl cotransporter to bring ions like Na+ and SiL into the cell. Water then follows these solutes osmotically, and the cell volume recovers. This is called regulatory volume increase, or RVI.
Okay, RVI when shrinking. What about swelling?
If a cell finds itself in a hypoosmotic environment, like the ECF gets too dilute and starts to swell, it does the opposite. It activates pathways for solute efflux. It might open specific K+ channels and Cl channels or activate a KCl cotransporter to let K+ and Cl leave the cell. Water follows these solutes out, and the cell shrinks back towards its normal volume. This is regulatory volume decrease, or RVD.
RVI and RVD. So cells actively fight changes in volume.
They do, over minutes. But there's a really important clinical implication here, especially concerning the brain.
What's that?
When the body is exposed to chronic hyperosmolality, like in severe prolonged dehydration or conditions like hyperglycemic, hyperosmolar state, and diabetes, brain cells adapt over hours to days. They don't just rely on RVI with ions, they start accumulating or synthesizing specific organic solutes inside themselves, things like sorbitol, inositol, betaine, taurine. These are called idiogenic osmoles.
Idiogenic osmoles,
Yeah.
to raise their internal osmolality.
Exactly. They raise their internal osmolality to match the high external osmolality, preventing severe shrinkage. Now, imagine you take someone in this state and rapidly correct their dehydration by giving them lots of dilute fluids intravenously.
Uh-oh. The outside becomes dilute quickly.
But the brain cells are still packed with those idiogenic osmoles, which they can't get rid of instantly. So now the inside of the brain cells is way more concentrated than the outside. Water rushes into the brain cells.
Leading to brain swelling. Cerebral edema.
Exactly. Severe, potentially fatal cerebral edema. That's why chronic hyperosmolar states absolutely must be corrected slowly and carefully in the hospital, allowing the brain cells time to shed those accumulated osmoles.
That's a critical point. Okay, this brings up osmolality again. You also hear the term tonicity. Are they the same thing, or is there difference? They sound really similar.
They sound similar, but they are critically different. This is a key concept.
Okay, break it down.
Osmolality refers to the total concentration of all osmotically active solute particles in a single solution. We measure it in osmoles per kilogram of water. Your plasma osmolality is normally around 290 mL/MK.
Okay, total particles in one solution. What's tonicity?
Tonicity, or sometimes called effective osmolality, is always a comparison between two solutions separated by a membrane specifically, a cell membrane in physiology. And crucially, tonicity only considers the concentration of solutes that cannot easily cross that membrane, the impermeant solutes.
Only the ones that can't cross. Why?
Because only the impermeant solutes exert a sustained osmotic pressure that causes water to shift across the cell membrane and change cell volume in the long run.
Can you give an example?
Sure, think about urea. Urea is a small molecule that can cross most cell membranes relatively easily using urea transporters. So if you add urea to the extracellular fluid, raising its osmolality, what happens to the cell?
Well, water should leave initially, right? Because the outside is more concentrated.
Initially, yes, the cell will shrink transiently. But then, urea starts to enter the cell down its own concentration gradient. As urea enters, the cell's internal osmolality rises, pulling water back in. Eventually, urea equilibrates across the membrane, and the cell returns to its original volume. So adding urea increases ECF osmolality, but it doesn't change the cell volume long term, meaning it doesn't contribute to tonicity. Urea solutions are isosmotic, but hypotonic.
Ah, because it permeates. What about something that doesn't permeate?
Like mannitol, a sugar alcohol sometimes used clinically, mannitol cannot easily enter cells. If you add mannitol to the ECF, that raises the ECF osmolality and its tonicity. Water leaves the cell and the cell shrinks and stays shrunk because mannitol can't get in to balance things out. So mannitol exerts a sustained osmotic effect.
So tonicity is about the non-permeating solutes that cause lasting water shifts.
Precisely. Clinically, when we estimate the tonicity of the ECS, we primarily look at the concentration of sodium and its associated anions like chloride and glucose, if levels are high, as it enters cells slowly without insulin. We specifically do not include BUN, blood urea nitrogen, which reflects urea concentration because urea is considered a permanent solute.
That makes sense. Sodium and glucose determine tonicity, not urea.
Right. And this leads to a really fundamental principle for understanding fluid balance in the whole body. Your total body sodium content primarily determines your ECF volume. Think about it. Sodium stays mostly in the ECF and holds water there. More sodium, more ECF volume.
Okay, sodium controls ECF volume. What about osmolality?
Your total body water content primarily determines your overall body osmolality. Adding or removing pure water changes the concentration of everything.
Can you illustrate that?
Sure. Imagine you infuse isotonic saline, 0.9% ACl, which has the same tonicity as body fluids. Sodium and water are added in proportion. Where does it go? Mostly into the ECF, because sodium stays there. So ECF volume expands, but ICF volume and overall osmolality don't really change.
Okay, isotonic saline expands ECF. What if you add pure water, like drinking a lot?
Pure water has no solutes. It distributes throughout total body water, proportionally between ECF and ICF, mostly ICF since it's bigger. So total body osmolality drops, ECF volume increases a bit, and ICF volume increases significantly. Cells swell.
Okay, and what if you add pure NaCl, like eating salt tablets without water?
Now you're adding solute without water. The salt stays in the ECF, raising ECF osmolality and tonicity. This pulls water out of the ICF by osmosis. So ICF volume shrinks, ECF volume expands, and overall body osmolality increases.
That really clarifies how sodium and water affect the different compartments.
It's a cornerstone for understanding fluid therapy.
Okay, we've covered single cells brilliantly. Now, let's zoom out. How do entire sheets of cells, like the epithelia lining your gut or kidney tubules, manage transport of solutes and water to control the body's internal environment, the milieu intérieur, as they say?
Right. Epithelia are fascinating. They're basically uninterrupted sheets of cells that are stuck together by specialized connections called tight junctions.
Tight junctions, what did they do?
They do two main things. First, they act like a selective fence or barrier between adjacent cells, controlling how easily substances can sneak through the gaps. Second, and really importantly, they divide the individual epithelial cell's membrane into two distinct domains or regions.
Two regions.
Yes. There's the apical membrane, which faces the lumen, or the outside world, like the inside of your gut or kidney tubule. It's also sometimes called the mucosal or luminal membrane. And then there's the basolateral membrane, which faces the underlying tissue, the blood supply, and adjacent cells. It's sometimes called the serosal or peritubular membrane.
So the tight junction is like the dividing line between the top front surface and the bottom back side surfaces.
Exactly. This separation of the membrane into apical and basolateral domains, each with potentially different proteins embedded in it, is called polarization. And it's absolutely key.
Why is polarization so important?
Because it allows for vectorial transport. That means the epithelium can move substances directionally from one side of the sheet, say the lumen, to the other side, the blood, or vice versa. It's not random, it's directed movement across the whole layer.
Vectorial transport, okay. Are all epithelia the same in how they do this?
No, there's a broad classification based on how sealed those tight junctions are. We talk about Tight epithelia versus leaky epithelia.
What's the difference?
Leaky epithelia, like you find in the small intestine or the proximal tubule of the kidney, have tight junctions that are, well, relatively leaky to ions and water. They have low electrical resistance across the sheet. These epithelia are designed for bulk transport, moving large amounts of fluid and solutes, often in a way that's nearly isosmotic, meaning the fluid transported has about the same osmolality as the fluid left behind. They use both pathways for transport. Transcellular, movement through the cell crossing both apical and basolateral membranes, and pluricellular, movement between the cells, sneaking through those leaky tight junctions.
So leaky epithelia do bulk transport using both routes. What about tight epithelia?
Tight epithelia, like in the collecting duct of the kidney or the urinary bladder lining, have very restrictive tight junctions. They have high electrical resistance. Their job is often to generate or maintain large concentration gradients for ions, or large osmotic gradients. They prevent things from leaking back easily. Because the pericellular pathway is so restricted, they rely much more heavily on the transcellular pathway to move specific substances.
So tight epithelia are better for creating steep gradients, mostly moving stuff through the cells.
Precisely.
Okay, so how do these polarized epithelial cells actually direct the transport? How do they make sodium go in from the lumen and out towards the blood, for example?
They do it by being very clever about where they put their different transport proteins. Remember all those channels, carriers, and pumps we talked about? Epithelial cells strategically place specific transporters on the apical membrane and different ones on the basolateral membrane.
Ah, the polarization again.
Exactly. For instance, that crucial NAK pump. In virtually all transporting epithelia, it's located almost exclusively on the basolateral membrane.
Why is that important?
Because by pumping sodium out across the basolateral membrane into the interstitial fluid and blood, it keeps the intracellular sodium concentration low. This, in turn, creates that strong, inwardly directed electrochemical gradient for sodium at the apical membrane, facing the lumen.
And that apical sodium gradient can then power other transport.
Exactly. It's the driving force for many epithelial transport processes. Let's look at a few classic examples.
Okay.
Consider NAN plus absorption, like in the collecting tubule of the kidney. This is often called the Using model. Here, you have specific sodium channels, like ENAC, only on the apical membrane. Sodium flows passively into the cell through these channels, down its gradient.
Okay, sodium enters apically.
Then, the NANK pump on the basolateral membrane actively pumps that sodium out of the cell into the blood. So net movement is apical to basolateral absorption.
And what about chloride? Doesn't charge need to follow?
Good point. The movement of positive sodium charge across the cell makes the lumen slightly electrically negative compared to the blood side. This electrical potential difference can then pull negatively charged chloride ions passively across the tight junctions via the pericellular pathway following the sodium. So you get net NaCl absorption.
Clever. Okay, what about secreting something like potassium?
Sure, in some parts of the kidney, the goal is K plus secretion. These cells still have the NaK pump on the basolateral side, bringing K plus into the cell. But then they place specific K plus channels on the apical membrane. Now, potassium flows passively out of the cell through these channels into the lumen, down its electrochemical gradient. Result, net K plus secretion.
So just changing which channel is on which membrane reverses the net direction for K plus brain.
Precisely. Let's take glucose absorption, like in the small intestine or proximal tubule. Here, the apical membrane has the Na plus glucose cotransporter, SGLT.
The secondary active transporter we talked about.
Right. It uses the sodium gradient to pull glucose into the cell, even against a glucose gradient. Now, the glucose concentration inside the cell is high, so on the basolateral membrane, the cell places a facilitated diffusion glucose transporter, GLUT. Glucose then flows passively out of the cell via GLUT down its concentration gradient into the interstitial fluid and blood. Result, efficient glucose absorption.
SGLT in, GLUT out. Got it. One more. How about secreting chloride, like in the airways?
Good example, very relevant to cystic fibrosis. For Cl secretion, like in intestinal crypts or airways, the setup is different again. On the basolateral membrane, you often find the NaKCl cotransporter, NKCC1. This uses the sodium gradient to bring Na plus K plus high and Cl into the cell from the blood side.
So chloride accumulates inside the cell.
Yes. Then on the apical membrane, you have chloride channels, like CFTR. When these channels open, chloride flows passively out of the cell into the lumen, down its electrochemical gradient. Sodium often follows pericellularly to maintain electroneutrality. Result, net NaCl secretion into the lumen.
And if CFTR is broken, that chloride secretion is blocked.
Exactly, leading to the problem seen in CF. So you see, it's all about the specific placement of transporters on the apical versus basolateral membranes.
That makes perfect sense. And water in all these cases, does it just follow the solutes being moved?
That's the fundamental rule for water transport across epithelia. Water movement is passive and always follows solute movement in response to osmotic gradients created by that solute transport. Wherever net solute goes, water tends to follow to keep things osmotically balanced.
Even in those leaky epithelia doing bulk transport where the fluid moved seems isosmotic.
Yes, the current thinking on isosmotic fluid absorption, like in the proximal tubule where huge amounts of salt and water are reabsorbed without a measurable osmotic gradient between lumen and blood, involves a couple of ideas. One is that the epithelial cells have extremely high water permeability thanks to abundant aquaporins, so even tiny transient osmotic gradients are enough to move lots of water.
Okay.
Another idea is the concept of local osmosis. Solutes pumped into the narrow spaces between cells, the lateral intercellular spaces, might create small, localized regions of hyperosmolality there. These local hyperosmotic pockets then draw water across the cells or through the tight junctions into these spaces before the fluid equilibrates as it moves towards the blood.
So tiny gradients or super high permeability allows isosmotic flow.
That's the idea. And one final crucial point about epithelial transport. It is highly regulated.
Meaning it can be turned up or down.
Exactly. The body needs to adjust absorption and secretion based on its needs. So epithelial cells can regulate transport in several ways. They can change the synthesis or degradation of transport proteins. For example, the hormone aldosterone increases the number of Na-K pumps and apical Na+ channels in kidney cells, boosting sodium reabsorption.
Okay, make more or less transporters.
They can recruit existing transporters from storage pools inside the cell and insert them into the membrane when needed. For example, histamine causes HK pumps stored inside gastric parietal cells to move to the apical membrane to secrete acid. Or insulin causes GLUT4 glucose transporters to move to the membrane in muscle and fat cells.
Move them to where they're needed.
They can modify existing proteins, often through phosphorylation or dephosphorylation, to change their activity, like how cyclic AMP-dependent phosphorylation activates the CFTR chloride channel.
Flip a switch on the protein.
They can even alter the permeability of the paracellular pathway by modifying the tight junctions themselves.
Adjust the leakiness between cells.
And of course, transport rates can be influenced by the availability of the transported substance in the lumen. It's a dynamic, adaptable system.
Wow. Okay, we have navigated in an incredibly intricate world today, from the tiniest pores and pumps in a single cell membrane up to the coordinated action and regulation of entire epithelial sheets. It really is mind-boggling how precisely your body manages all these fluids, ions, and volumes every single second.
It really is. This deep dive, I hope, highlights how every single cell is, in its own way, a master of balancing these forces and flows. And understanding these fundamental mechanisms is just absolutely essential if you want to unravel the complexities of health and disease.
Yeah.
Remember, these are the very processes that underpin how your body responds to everything from just taking a sip of water, to processing a meal, to responding to critical medical interventions like IV fluids or diuretics.
So what does this all mean for you, our listener? It means you're building an absolutely rock-solid foundation for your medical and physiological understanding. You're part of the Deep Dive family, and we absolutely know you are capable of mastering this material. It's complex, but you can do it.
Definitely. Keep asking those questions. Keep trying to connect the dots between these different transporters and processes. And remember, the more you explore physiology, the more truly incredible the human body becomes.
Couldn't agree more. Until next time, keep diving deep.
And maybe consider this as you go. How can just a seemingly minor alteration, maybe a single mutation, affecting the function of just one type of ion channel, lead to such widespread and sometimes devastating diseases throughout the entire body? It really reinforces the incredible interconnectedness of all these systems we've discussed today.